that comes out to be equal to about 0.318. In 1989, Newsweek reported that 60% of young children have blood lead levels that could impair their neurological development. Assuming that a class in a school is a random sample from the population of all children at risk, the probability that more than 3 children have to be tested until one is found to have a blood level that may impair development is equal to what? So what we have here is a situation where we're waiting for a success. We aren't given a particular number, a fixed number of trials and asked to determine the probability until we get a success, but rather we are waiting for a success. So what we have to consider is that this satisfies bits, not bins. Bits, the only difference between it and bins is that it's often called the wait time distribution, and it refers, it doesn't have a fixed number of trials like N does, but rather you are counting the number of trials until you get a success. Okay? So let's picture this scenario. Assuming that a class in a school is a random sample from the population of all children at risk, the probability that more than 3 have to be tested. Well, that means that the first 2 that were tested, or actually the first 3, because it said more than 3, did not have blood levels that may impair development. But sometime thereafter, the 3rd or the 4th or the 5th and so on child did have blood levels that impaired neurological development. So let's alter this question first a little bit by identifying, okay, first, just what's the probability that it won't be until the 4th child in a sample, it won't be until we pick that child that one is found to have blood levels that may impair development. Okay, so we finally want a success on the 4th child. Well, with the geometric setting, we have to factor in that if we didn't succeed until the 4th trial, that means that we succeeded on the 4th, but we did not succeed on the 1st or the 2nd or the 3rd. So the probability that the first child was did not have blood levels that would impair their judgment or their development was 0.4. It's just the complement of the probability that it does. The probability that the second child does not have impaired judgment or development is also 0.4. The probability that the third child does not have impaired neurological development is also 0.4. But finally, on the 4th child, we have a child that does have impaired neurological development, and that probability is 0.6. So with bits, the requirement is that the trials are independent, and we can assume that children selected have independent blood levels. And so, therefore, we can find the probability that the first is not impaired, and the second is not impaired, and the third is not impaired, and the 4th is impaired by multiplying those together. So our probability will be 0.4 to the 3rd power times 0.6. Now, to get at the question that's actually asked, what's the probability that more than 3 have to be tested until one is found to have a blood level that may impair development? We want to remember that there's a shortcut. The probability that x is greater than n in a geometric setting, where n is the trial on which we get success, we take the probability of failure, 1 minus p, and raise it to the nth power. We want success after the 3rd trial. So we're going to take the probability of failure, 1 minus 0.6, and raise it to the 3rd power. And we'll have the probability that we reach a success after the third trial.